Hello students, welcome to Shruti Academy. So let us start with another topic of electrical engineering, which is the maximum efficiency. We have already seen the expressions for the full load efficiency and the efficiency when the load is fractional. Okay, so we have seen the formula for the efficiency is given by output upon input, and in terms of losses, output upon output plus losses. So the efficiency is given by V2 I2 cos phi 2 upon V2 I2 cos phi 2 plus Pi plus PCU. Pi is the iron losses and PCU is the copper losses. So copper losses are given by I2 square I square R losses. So here RE2 refers to the resistance referred to the secondary side. RE2 is the resistance referred to the secondary side. So now let us start finding out the maximum efficiency and the conditions for the maximum efficiency. At what condition we get the efficiency to be maximum? We will be deriving and calculating those conditions over here right now. Okay. So for that we will be taking this expression and we will be differentiating it with respect to I2. In case you are taking the formula in terms of the input power, so that means in case you are taking the formula where the output is given by input minus the losses, or you can say the efficiency equal to 1 minus the losses upon the input power, then in that case you need to differentiate it with respect to I1, the input current. But since we are taking the efficiency in terms of the output, so we are differentiating in terms of I2, that is the secondary current. Okay. So we will be differentiating it and we will be equating to 0, because in order to get a maximum value, the differentiable part should be equated to 0. Then we will be getting the condition for the maximum efficiency. So we will be equating it to 0. It is to be 0 for maximum efficiency. Okay, so now this is in the form of U upon V. Okay, so whenever we take the differentiation of in any of the terms U upon V, we get the formula that first we differentiate U with respect to T, then we write V as it is. Okay, then we put a minus sign, then we put V as it is. We differentiate V with respect to T, put the numerator as it is. Okay, and in the denominator we do the squaring, so it will be V square. Okay, so it is V. Okay, so we'll be applying this formula in order to differentiate it. We are taking this formula for the efficiency over here. So before that, we will be dividing with I2. We will be taking common I2 from numerator as well as from denominator. So our efficiency will be becoming V2 cos phi 2, I2 we are taking common. Okay, so from here also it will be V2 cos phi 2 plus Pi upon I2 plus I2 RE2. So this I2 and this I2 gets cancelled. So now we are left with this expression. We need to differentiate it with respect to I2. Okay, so let us start differentiating it. So first we will be differentiating the numerator and keeping the denominator as it is. But since the numerator is having no term of I2, so it is a constant. So we can directly put 0 over here into the denominator will be placed as it is. Okay, putting a negative sign over here, then we'll be getting over here, we need to differentiate this denominator and the numerator will be kept as it is. Okay, so differentiating this term would again give us 0 because it is a constant. Okay, so we'll be getting over here 0 plus, it is 1 upon I2, that means I to the power minus 1. So the differentiation of x to the power n is equal to nx power n minus 1. Okay, so it is I to the power minus 1. So here it will come minus 1, x to the power minus 1, minus 1. So x to the power minus 2. Okay, so we'll be getting over here minus 1 pi and I2 to the power minus 2. Then over here it is I2. So the differentiation of d upon dx x is always 1. Okay, so it will be 1 into RE2. So here it will be plus RE2 and it is multiplied by the numerator as it is u. So our u is V2 cos phi 2. Okay, so I'm closing the bracket over here and upon is the denominator square. So our denominator is V2 cos phi 2 plus pi upon I2 plus I2 RE2 whole square. Okay, in the denominator it is whole square. So this forms our expression for d efficiency upon di2. Okay, d efficiency upon di2, this forms a whole expression. Now we need to equate it to 0 in order to find out maximum efficiency, in order to find out maximum value. So d eta upon di2 should be equal to 0. So in order to get 0, this term will be 0. So the denominator has no significance. Here the numerator should be 0. This whole term is 0. 0 multiplied by anything is 0. So this whole term is 0. So let us mark it to be 0 over here. This whole term is 0. So we are left with this term. So over here it is minus pi upon I2 square. I2 square. Okay. Plus RE2 into V2 cos phi 2 should be equal to 0. Should be equal to 0. The denominator, when it will be multiplied by 0, this will be whole equal to 0. When this denominator will be multiplied by 0, then it will be automatically becoming 0. So we are left here with this term equal to 0. That means we are left with this. Now V2 and cos phi 2 are the constants. They are the constants. So they will be going over the next side to the next side with the denominator, in the denominator, and it will also become 0 because this is all the constant. This is V2 cos I2 is the constant term, okay, so it will be also zeroed. So now ultimately we are left with minus pi upon I2 square plus RE2 equal to 0. So we are left with minus pi upon I2 square plus RE2 equal to 0. So this can go that side with a positive sign. So we will be getting over here RE2 is equal to pi upon I2 square. So pi will be equal to I2 square RE2. So we from here we are getting this relation, and this relation shows that iron losses are equal to copper losses. I2 square RE2. I square R losses are always the copper losses, the variable losses, and the Pi is the constant losses. Those are the iron losses. So in order to get the maximum efficiency, the condition is that the iron losses should be equal to the copper losses. Iron losses should be equal to the copper losses. This is the condition in order to get the maximum efficiency. Okay. Now we can put the iron losses to be equal to the copper losses and we can get our value. So the maximum efficiency expression would be eta max would be equal to x into VA rating into power factor upon x into VA rating into power factor, okay, and plus 2 pi, because copper losses Pi is equal to the iron losses. So I can put in the place of copper losses, I can put the value of iron losses also in order to get my maximum efficiency. So this would give me my expression for maximum efficiency. Now, if we draw a curve relating to the efficiency and the load, that means the load current, then the curve which we will be getting would be somewhat like this. It would be getting somewhat like this. This shows my efficiency and this shows my load. Okay, this shows my load. This is the maximum efficiency value. So this load corresponds maximum efficiency. So when the load is low, when the load is not high, the efficiency is also low. But as gradually the load increases, we can see the load is increasing like this. The efficiency is also increasing and it reaches a maximum value where the copper losses are equal to the iron losses, where the iron losses are equal to the copper losses, and that point is denoted over here. And when the load is more increased, then the efficiency starts decreasing, not increasing. So this is the nature of the efficiency and load of a transformer. So till maximum efficiency, the efficiency increases when we are increasing the load. And once the maximum efficiency is attained, even when the load is increased, the efficiency starts decreasing. So this is all about the maximum efficiency. So in the next lecture, in the next session, we will be dealing with the expressions of the KVA and the load current. What would be the expression for the load current? What would be the expression of the fractional value of the load at the maximum efficiency? So till then, goodbye. So thank you. So please subscribe my channel. Please share my videos. And if you have any doubt, you can ask me in the comment section. Thank you.